So far in these discussions of organometallics, all we've done is talk about Grignard reagents. Well, there are other organometallics. Just leave that as organomet. So here's our reaction. We're going to take an aryl halide, we know how to make those, and we're going to react this with an aryl metal, and we know how to make those. We've talked about Grignard reagents. And we're going to react these in the presence of a palladium catalyst, and we're going to connect our two aromatic rings. Great. Well, now we need to recognize the M in metal is not always magnesium. Now, the M in metal can be magnesium. So if M equals magnesium X, like magnesium bromide, and there's always going to be another halide along with that, we call this the Kumada coupling. Okay, we haven't seen the mechanism. We'll see the mechanism shortly, but that's called the Kumada coupling. As it turns out, there are other variations of these couplings. They're not all Kumada couplings, so let's see some of the other ones. And the way they differ in terms of the coupling is what the identity of the metal is. So, what if the metal counterion is a zinc halide? Hold it, what? Did you say zinc? Yes, I did. You can use zinc in these. So, this is called a Negishi coupling. So what is it? How do you make this zinc aromatic thing as our organometallic? Well, we can start with a Grignard reagent, and let's just leave this X. We've seen those, and you can treat these with zinc salts, and essentially we're going to do a substitution. Our nucleophilic aromatic ring is going to attack. We're going to displace that bromide, maybe not a perfect mechanism, but close enough. And we're going to make a new aryl zinc, where this is our metal that balances our aromatic ring. This process is called a transmetallation. So we can substitute out one metal, in this case magnesium, and put in a zinc. And if we do that and use this organometallic species in our reaction at the top, we call this a Negishi coupling instead of a Kumada coupling. Well, as you might guess, there are other metals we can look at. There's a tin example, and let's just keep this simple and say it's a trimethyl. Tin bonds make 4 bonds, so what are the other bonds to? We'll make them to methyl groups. This is called the Stille coupling. In the 1980s, when everybody's listening to their new wave music and The Cure and the Smiths, the Stille coupling was all the rage. Everybody was doing Stille couplings. How do we make this? Well, again, we might start with a Grignard reagent, where this is a very easy organometallic to make. And then we treat this with some kind of tin reagent. Our nucleophilic aromatic ring will replace that chloride. And now we have an organotin reagent, where our metal is a trimethyl stannol group. One last one I want to talk about, where M equals boron. That's right, boron. And this is called, when you use a boron salt, it's called a Suzuki coupling. So, how do we make this? Same way as before. Let's get 2 electrons there. We start with something like a Grignard reagent, could be an organolithium reagent. This is not a perfect mechanism, but it's close enough for us. Benzene ring again attacks the boron. We're going to lose one of our OR groups off the boron. And this is now our metal. So these are different variations on exactly the same theme. What is the theme? Well, it's shown at the top of the slide. We have an aryl halide reacting with an aryl metal, and these two aromatic rings get stitched together to form our biaryl. As it turns out, there are lots of different metals you can use, and different metals give different, maybe one's a little bit milder, it doesn't destroy other functional groups, or maybe one works faster. And so there are different variations of this that people have developed. But all in all, they're the same reaction. These are all coupling reactions where we stick together two aromatic rings, one of which at the top is an aryl halide and the other is an aryl metal.